Hello and welcome to the second video of hazards in digital logic circuits. In this tutorial we'll talk about static 0 hazard. I highly recommend that you watch my previous video where I talk about static 1 hazard because the analogy is the same, it's just that the explanation is different. So when we are expecting a 0 at the output but we get a 1 momentarily by mistake, that is known as static 0 hazard. And when can such a situation occur? So that is what we are looking at in this video. If you consider this Boolean expression a dot a bar, which will always give us 0. The circuit for this is this. So we know that if we give a 1 here, we'll get a 0. If we give a 0, we'll get a 0. But what happens when you transition from 0 to 1? Let's look at that case. So we know that there is no problem when a is 1, a is 0, the output is going to be 0 nonetheless. But when a goes from 0 to 1, momentarily the inputs of AND gate will be 1, 1, producing a 1 at the output. You see, when you change from 0 to 1, this 1 gets here immediately. However, this one will remain there for some time because it will take some time to change to 0. You've gotten a 1 here, you'll eventually get to 0 here, but for some time this 1 will remain in sync with this other one, producing a 1 at the output, and that is known as a glitch. Irrespective of the value of a, whether it's 0 or 1, we were expecting a 0. We were expecting a 0 here throughout. But what happens was, when a changed from 0 to 1, we found a glitch. The circuit produced 1 momentarily. And when could that possibly happen? With the same example that we took in the previous session, now we are dealing with product of sum terms. So we'll pair zeros. So ideally you would have paired these two zeros and these two zeros, producing sum terms to be equivalent to these two, a plus b and a bar plus c. And when this special condition occurs, when b is 0 and c is 0, we get to a point where the output expression reduces to a dot a bar, which should always be 0. But that will not happen all the time, because when or if a will change from 0 to 1, we've seen that a glitch will occur, and that will not happen if a change from 1 to 0. And you could check that, because if 1 to 0 happens, a 0 will get here and that will keep the output 0 forever, irrespective of the propagation delay of this gate. But nonetheless, the glitch is here, so the circuit is hazardous. So how do you avoid static 0 hazard? Again, the answer is similar. You must avoid adjacent 0 not being included in the single sum term. So if there are adjacent zeros, these two are adjacent zeros but are not included in the single sum term, so you must include them in a single redundant sum term now. And that will increase the cost but will remove the hazard. So if we add this term here, b and c are added, b plus c is the additional sum term. So I add this. So whenever these two are zeros always, so the output of this AND gate will be 0. Whatever happening, whatever propagation delay is being generated here, it will not affect the output because these two will become non-deterministic. A 0 from here will permanently make this 0. So that is how you remove a static 0 hazard from the circuit, by making it more complicated, more costly, but sometimes to increase the efficiency of the circuit we need to increase the cost. That's a trade-off. Well, that was it for today's tutorial. I hope you liked it, and if you did, give it a thumbs up. I'll see you around. Take care. Bye bye.